In this presentation, we are going to look at linear models with R, analysis of variance and regression models, and so forth. In a study of the strength of pencil leads, standard length pieces of pencil lead were supported on two ends and supported at their midpoints. Samples of 5 pieces, each of 4H, H, and B lead were used, and the breaking stresses, load in grams, that's the technical units, at which each piece failed were recorded. The following data was given. The data was given below. Okay, so we have 4H here. Those are the measurements. H 99. Okay, 99.2 and so on. And B lead 46.7. Essentially, just in case you're wondering, 4H, H, and B is just the sort of how thick the pencil is, basically. So 4H is very narrow, B is very thick, okay, and H is somewhere in the middle, okay. Very faint is 4H. Okay, by the way, I'm Irish, so we say H here, not H, and I'm going to stick with that because we know what we're doing. Anyway, so what we're going to do here is create the data, and we're going to call it measurements, and I'm just going to collect up all of the measurements there. Essentially what I'm going to do is run an analysis of variance procedure on this data. So what I want to do is collect up all the data in a single vector, a numeric vector, but I want to also record what each observation corresponds to in terms of the categorical variable. So I have a categorical variable here, which is the pencil lead type, okay? So let's just collect those observations there, and those are the 4H observations, the first 5, the H observations, the next 5, and the last 5 is the B, okay? So, and also what I'm going to do is specify the pencil types, or lead types if you want. I just go pencil types because that's just what I'm sort of used to. What this does is just takes the input here, this particular command, and repeats it 5 times, okay? So the input here is 5H, 4H, so it just repeats that 4 times, just replicates it 4 times. And likewise for H, H even, and B, okay? So that creates 15, a vector of 15 names, which are the pencil types, okay? The first 5 are 4H, the second 5 are H, and then B, okay? Now, this is important going forward. This variable we just created, pencil types, if I just get the class of that using the command class, that's a character, okay? It's okay actually to proceed as long on the basis that it is a character, but really what we should be doing is actually using our full skill set here. So what I'm going to do is actually convert that into a factor, okay? That variable, and I'm also going to specify the levels. And in ascending order, 4H, H, and B. Now I think that would be the order that they would come in anyway if I didn't specify anything, because the default is alphabetical order, where 4 comes first. But anyway, this actually specifies the order, just in case you did want to specify a different order, okay? And now we have a factor called pencil types, okay? So that's a factor. So I just checked the class again, just to see, did I update everything the way I wanted? Okay. Now, I'm going to save these 2 variables, measurements and pencil types, in a single data frame called mydf. Okay. I don't really have to do this, but it's just to be consistent with further analyses on an ongoing basis that I'm going to take this step so you can match this up with working with other analyses on other data frames, okay? So anyway, perform an analysis of variance on the above data and determine whether there are any differences between the population mean breaking strengths of the pencil types. You are given that the assumption holds for all the assumptions are relevant and are valid for the analysis, that they're all ready to be, that we're ready to go essentially. Don't we have to check them, okay? So just get on with it. What we could do here is actually just check the box plots to see the relative distribution. This is a good visual analog of a visual complement to the analysis of variance, and just sort of see, is there a bit of an overlap there in terms of the distribution? And clearly there isn't. 4H and B are not too far from each other in terms of distribution, but we can see that H is quite far off. Okay, so it seems to be much higher. Okay, it's not even much of a box plot basically. It's just a line. Okay, that's what the box is. It's just the main set of values is so close. Anyway, so the command is AOV, analysis of variance. Measurements is the response variable, and the categorical variable, which is essentially our predictor variable, in other words, is pencil types, and we just specified the name of the variable of the data frame that we're working from. Okay, so this is numeric variable, this is the factor or the categorical variable. So this just has it all set up for us, and this is the output that we would get. And the ANOVA table is there, standard residual error, residual standard error, and so on. It's not very easy to look at, but we'll just continue on anyway. By the way, we don't really need to specify, just as a quick remark, this is a bit unnecessary to add in this part. The reason is because we've actually inputted pencil types and measurements into OR directly, that they're there in memory, so they're in the environment anyway. But that's just a sort of happens to be that would have this would work basically without that piece of code, because we created the measurements and pencil types before we created data to MyDF, the data frame. But let's just sort of keep it in a certain way that's consistent going forward. Okay, so that's the way we're going to do it. Now, I'm going to call this model my AOV model, my analysis of variance model. I'm going to save it as a data object, okay, and let's get the summary of it. So this gives us the ANOVA table, okay. Degrees of freedom, sums of squares, mean square error, the test statistic, which is the F value, and then finally the P value, okay. So it's a really small P value, and there's 3 stars beside it, which means it's highly significant. So working on the basis of, let's say, we usually sort of say 5%, and is that less than 5%? Of course it is. There is a significant difference between the groups in terms of the mean breaking point, okay, the mean measurement, and that is sort of what we were getting at there. We could sort of see that H is very different from the rest. Now, just actually, that's a sort of the analysis of variance done. Now, there's one more exercise to do. Let's just check how well these do. This model does fit the data, okay? And are the assumptions met? Something we can do is we can plot the model, okay? Now, just what I'm going to do here is actually specify which equals 1. And I get this fitted value versus residual plot. Now, honestly, there's not a whole lot of data in it, so it's not going to be that great to look at, but it's sort of good practice to do this and just sort of see, is the values, the scatter plot points here, are they sort of relatively well distributed around the data? Is there any constant variance? In the case of ANOVA, so to speak, they would be grouped up like that, so that's not such a big deal. The fact that they're in a line there, it's just the way it works for ANOVA models, okay? Which equals 1, just actually specify which of the 6 plots do you want, okay? So you just go which equals 1, 2, 3, 4, 5, or 6. And here, just to make this plot easier to read, I just added in these additional specifications. Plot character equals 18, just give that little diamond there. Color equals red, and CEX equals 2, that's just the plot character size, just to make it a little bit easier to read. We note that the average line sort of closely follows the 0 level, which is good, okay, very good actually. So we want that red line to be around the 0 mark. That's the average, so to speak, the average residual point line. Okay, this is the second of the plots. It's a QQ plot for the residuals. Now, this is always going to be challenging in the context of analysis of variance models, because it's not really as well suited for it. This plot is not as easy to read, but essentially the points there do more or less follow the trend line. So we're going to take that and move on. Okay. So next thing is carry out a post hoc analysis to obtain confidence intervals for the pairwise differences between the population mean breaking stresses of the three types of pencil lead. Okay. So the post hoc test, after a multivariate test such as ANOVA, it is often desired to know more about the specific groups to find out if there are significant differences or not. This step after analysis is referred to as post hoc analysis and is a major step in the hypothesis testing process. One common and popular method of a post hoc analysis is the Tukey tests. This is known by several different names. This test compares all of the means of all of the treatments, in this case that's the pencil types, to the mean of every other treatment, all the other pencil types, and that's essentially the treatment here is the sort of the general name in statistics for the factor, the treatment essentially, and is considered the best available method in cases where confidence intervals are desired or if sample sizes are unequal. Okay. So how do we go about this? So this is an inbuilt command in R, Tukey HSD, okay, is a function in base R available to and takes a fitted AOV object which we have saved. So this is our AOV object, and we're going to apply this command here to get our confidence intervals, Tukey HSD. We're going to save that as tukey.test, okay, and when we run it, we get Tukey's multiple comparisons of means and a 95% family-wise confidence interval. Okay, so there's quite a lot in this about where these come from. This family-wise, that's a very loaded phrase. But we'll just sort of keep going with it for the time being. What we're interested in really is the upper and lower bound. So this is the difference between H and 4H. Now I'm saying H. Anyway, we'll go along with it. The average difference there, the mean difference, or the expected value of the differences is 41.02, and that's a confidence interval for that difference. So that's obviously significant, and we can tell by that adjusted p-value. In the second case, B and 4H, the expected difference is 7.10, but the confidence interval goes from minus 2.38 to 16.58, and in that case, that is not a significant difference. B and H, minus 33.92 to minus 43.40. Again, that's the confidence interval is that, minus 43 to 24, and that's the expected value, minus 33.92, and again, that's also significant. Okay, so there are significant differences between H and 4H and B and H, but not a significance between B and 4H. So in conclusion, yeah, that's what I just sort of said there really. The confidence levels and p-values show significant between group differences for the pairings of 4H and H and B, but no significant difference between 4H and B. Now, what we can also do is plot that, Tukey.test, plot.tukey.test, and this gives us a visual analog of this table here. So this gives the difference and the upper and lower bound of the intervals. That's essentially what those vertical lines mean. Okay, so here we have the pairings for each comparison, H and 4H, B and 4H, and B and H down here. So the upper and lower bound of this component here is essentially the upper and lower bound of the confidence interval with the expected difference there in the middle. Okay, so that's it. So we could tell that B4H is transecting the vertical line down here, which is the 0 line. Okay, so that's it. Alright, we'll leave it there.